Well, welcome everyone. Can everyone hear me? Okay. So I want to thank you all for coming here today. Let me first say that I realize that chemical engineering has a reception here starting in about 15 minutes. So it really gets hopping about 3:30. So I'm not going to be offended if you need to get up and leave. And I know some others here have a reception to go to pretty soon this afternoon. So as you need to leave, please go ahead. I want to start by thanking Dean Ken Galloway in engineering for nominating me for this to represent the School of Engineering. It's quite an honor for me to be selected from among so many very talented faculty to give this presentation to you today. I also want to start by really thanking all the students and so who have worked on this project. First off, my collaborator David Cliffel in the Department of Chemistry. Dave and I have been working on this project for several years, and it's been a lot of fun. I think you'll see some of the challenges we've encountered as we've gone along. Professor Kirill Bulletin in physics is just a recent collaborator of ours, just starting to really do some really exciting things with graphene. The Ph.D. students who've worked on this project, Peter Cizelski graduated about 10 months ago, 9 months ago. Chris Faulkner about a year ago. Gongping Chen and Gabriel LeBlanc are current Ph.D. students on this project. The bachelor students, undergraduate students who've been involved, Matt Irwin, senior, who's here today, Fred Hijazi, Amanda Scott, and they've all been co-authors on some of our recent papers on this project. Also, we've been funded financially by the National Science Foundation through 3 different programs. There. So to start off, just a little bit of an outline to let you know basically what I'm going to be talking about today. I'll start with a way of quantifying the energy crisis and called basically the Terawatt Challenge. From there, I will move on to a very brief primer on photosynthesis. And then kind of give you a historical perspective of this project over the past 7-8 years and some of the challenges we've faced and some of the obstacles that we have been able to pass through. Also, I'm going to mention I'm going to give a little bit of motivational lessons in here too. I know the seniors in chemical engineering know what I mean when I say motivational lessons. You may call them demotivational lessons, but I tend to have that kind of sense of humor, and I will insert those as appropriate as they blend with the talk, and they're also my parting message for the seniors here today. And finally, a little bit of future directions at the very end to give you an idea of where we're going on this project in the next few years. So to start off with, the Terawatt Challenge. Okay, so a terawatt refers to 1 trillion watts. All right, and you can think of a watt here basically as a rate of energy. Okay, so if you globally looking at planet Earth, the global power demand, the rate that we're using energy is around 15 terawatts right now, and 85% of that energy demand comes from fossil fuels. Now the bad news here is if we look at the projected power demand for 2050, which really corresponds to, I think, the career of the seniors who are in the room today here, from starting now until getting them close to retirement. The projected power demand is supposed to double to around 30 terawatts. Okay? This is largely due to increasing world populations and industrialization of third world countries. Now, this is a little bit chilling because of the fact that we're currently using 85% from fossil fuels. And the real question is, how do we get there without bankrupting our economy and then destroying our environment in the process? And so I've put the picture here. Does anyone recognize this? It kind of dates me a bit. Yeah, Mad Max. If you'll recall in some of those Mad Max movies that, they have violent encounters and battles and lots of death over just trying to get a gallon of gasoline or a gallon of fuel. Okay, so because is that where we're headed if we don't come up with solutions to this energy problem? Now, if you look at all the alternative energy options that are out there, they all could end up chipping in a little bit. Okay, what I've listed here is the practical potential. So the potential amount of terawatts we could get from these different alternatives, and it ranges typically from a couple in hydroelectric to maybe up to 5 to 8 for wind. But you'll notice down there at the bottom that solar has an incredible capacity. Okay? So 60 terawatt capacity for solar. And if we compare, I'll also talk a little bit about solar versus biomass. In the case of biomass, it's really got the limitation that it's limited by land and land area. Okay? You're using the sun then to ultimately grow crops. The crops pull carbon dioxide from the air and then release it back when you combust them for the energy or the fuel. Okay? In the case of solar, the idea is, can we use the sun more directly? Okay? If you look at biomass, we're talking about 1 gallon of gasoline per acre per day for something like switchgrass, which grows pretty rapidly. Okay? And so can we ultimately get around some of these problems and ultimately use solar directly, and maybe even use solar directly through plant-type sources? Okay? In fact, planet Earth has a solar energy conversion system right now that is an order of magnitude greater output than our usage of fossil fuels, and that's through photosynthesis. So I put a quote here from George Whiteside, who's a prominent chemist at Harvard University. He happens to be my academic grandfather. And George says that basically plants connect humankind to the sun, to our ultimate source of energy. And if you think about it, the sun is responsible for so much through plants that we're able to claim food, fuel, building materials, our feedstocks, and fibers for clothes. So through these plants that get their energy from the sun, we have a lot of materials to work with here. Now, the question I'm going to pose today is, what about the renewable energy? Can we take the components of plants that drive photosynthesis and use them toward renewable energy solutions? So to kind of get that started, let's consider a little bit about photosynthesis and how photosynthesis works. So first off, I show here a leaf. And in the cells of the leaf here, we have basically the chloroplast. And inside those chloroplasts, breaking those down, you have kind of the granum or stacks of thylakoids. And so the thylakoids, then breaking that down a little bit further, will actually contain the lipids that then surround the key proteins that carry out photosynthesis. And on the left there, we have Photosystem II, which splits water. Okay? And then as you move over to the middle, we have Photosystem I. And Photosystem I basically achieves a volt, a little over a volt across that 10 nanometer space of that membrane there. Okay? And Photosystem I ultimately creates that chemical energy that drives photosynthesis. And we're going to be talking a lot about Photosystem I today. In fact, that's the focus of what we're going to be doing in trying to develop solutions here for solar cells that are biologically inspired. This is Photosystem I in a kind of a crystal structure. And so I first show that the chlorophylls around the outer edge of Photosystem I, a little bit of its structure there, it's a big protein. You know, from a molecular perspective, it's a monster. It's about 500,000 molecular weight. But keep in mind that the size is only about 10 nanometers. So it's still technically a nanoparticle for all practical purposes in how we work with it and treat it. Okay. Here shows the electron transfer chain. We have a P700 reaction center down there at the bottom where basically light is funneled to. You'll see that in a second as I keep going. And then at the top of the electron transfer chain, there is an iron-sulfur complex denoted as Fb. Now let's see really how this works in nature. So in nature, we have Photosystem I here sitting in a membrane. And light comes in, basically collected or grabbed by the chlorophylls, and funneled down to the P700 reaction center. And when this happens, P700 goes to an excited state, P700 star. And it hits that excited state, it will transfer an electron to the other side of the protein, to the terminal Fb, the iron-sulfur complex there. Now, in a plant, what's going to happen is ferredoxin is going to come in, pick up that electron, and take it off. Now, with the chemical energy to carry out another cascade of events that continue us through photosynthesis. But we now have to reduce back P700. And that's done by a copper-containing protein known as plastocyanin. delivers an electron to P700, and now more light can be captured, and this process can be repeated a number of times. Okay. So one of the highlights of Photosystem I, it has a quantum efficiency of greater than 97%. Now, let me put that in some kind of framework. What that really means is a quantum efficiency is basically referring to of the light it captures. It is incredibly efficient at using that light. Okay? So for every, let's say, 100 photons of light that are captured here, we're going to have 97 electrons that are going to be sent out the other side, at least, in the case of Photosystem I. The other thing is very fast. Charge separation here occurs in about 15 picoseconds. It's 10 to the minus 12 seconds. And then we have a 1.1 volt potential, as I mentioned earlier, across that really thin 10 nanometer space. So quite remarkable properties of Photosystem I, which led us to the question, can we take it out of a plant and then use it for a photoconversion device? Okay? Basically stripping it out of the plant, putting it on an electrode, and then trying to go through some of the same steps that happen in photosynthesis, but on a surface. So here we show proteins on a surface, and we're treating this kind of like a plant environment, an aqueous environment. We're putting this in an aqueous solution. For a lot of the work I'm going to tell you about today, that's what we do. We put in molecules that can pick up electrons from the protein, and we're using the electrode to ultimately donate or pull away, as the case implies, electrons from the protein. So here is the protein. This would be the process that happens. Light comes in, funneled down to the P700 reaction center. P700 goes to excited state. Electron is sent to the other side of the molecule, and we're able to then pick that electron up. Instead of using ferredoxin, as happens in a plant, we're going to use a small molecule mediator that can move around in solution and rapidly pick up these electrons. And then we have to get an electron back into P700 plus to reduce it back to P700. So basically, we're using a gold electrode here as plasticyanin to donate the electron into P700 plus. We are using a small molecule that can pick up electrons from the FB side of PS1 as ferredoxin in the plant. Okay? So we're kind of making those two substitutions, and then ultimately trying to assemble these cells. This just shows you that, indeed, you can treat PS1 like a solar cell, where I show here current as a function of time. We have a background case current where the lights are off initially. We turn the light on, you see current go up. We turn the light off again, and current comes back down. I'll be showing you these types of curves a bit today. And these are basically called chronoamperometry curves, but we're using them to ultimately shine light and see increases in current. Make sure that our system is working as we expect. Now, I want to talk a little bit about the long-term challenges in this project. Now, by long-term, I don't mean something that we have a solution to right now, something that we've already solved, something that we're working toward, and it may take a few years to get there. The first long-term challenge I'll identify here is it would be really nice to ultimately approach the quantum efficiencies that PS1 has in a plant. So I threw out that number earlier, greater than 97%. Can we take it out of the plant and get a 97% quantum efficiency, basically meaning of the light that we're absorbing, are we going to be able to use that at a 90% efficient rate? Okay, that's a real challenge. There are many things we've got to be able to do, two of which are we have to take the protein out of the plant. We need perfect orientation of that protein on a surface. Okay? We also would need essentially perfect wiring at both ends of the molecule. We need to be able to make sure we can get electrons into the bottom part of the protein and out of the top part of the protein. Okay? So perfect wiring and perfect orientation is important. All right. So I put this up. Not that we're battling nature here. We're actually trying to harness and use nature to our benefit. But yes, in the battle between you and nature, it's hard to duplicate nature. Okay. Now, going to the second step here. What we'd like to be able to do for the next long-term challenge is, can we ultimately achieve greater overall efficiencies than the plant by ultimately increasing the light absorption? Okay. Now let me show you what I kind of mean by that here in the next slide. So this shows the light absorption versus wavelength for Photosystem I in the nice rainbow curve there. Okay. And so what you'll see is that PS1 absorbs well in the blue down there in the kind of 400, 450 range. It absorbs well in the red up here between 650, 700 range. And it doesn't absorb very well in the green. Okay? And that's probably what you would expect because plants are green. They're going to reflect green. Okay? So that's not a problem. That's just basically how PS1 absorbs. But what I want to mention to you is that if we compare PS1 to silicon, a common solar cell material, silicon's a dark gray color. It's going to absorb a lot of light in this region. Okay? It's not going to have a lot of these little valleys and things that I'm showing here for plant. So ultimately, we have to be able to increase the amount of light absorption we get out of these systems to really compete with silicon down the line. Now, is that impossible? No. This protein can be modified in a lot of ways. A lot of really talented people across the world are working on that, modifying the proteins to enable them to absorb more light. Okay? So this is something I ultimately see that can be solved, and I could see us then having greater overall efficiencies than plants, certainly, and then working towards internal quantum efficiencies as high as those in a plant. If we can do that, we'd be in really good shape. Finally, the other long-term challenge I put here, and one that we've just started working on, is to use Photosystem I in combination with Photosystem II to ultimately generate fuels. Okay? Certainly a really awesome fuel, if we could produce it in high volumes today, would be hydrogen. Okay? Think of the hydrogen economy. Think of fuel cells. We need a lot of hydrogen, and we need to get it through environmentally friendly ways. Okay? So I mentioned earlier to you PS2, Photosystem 2, as part of photosynthesis, splits water. Photosystem I can be modified in a way to actually take those protons from PS2 and then reduce them down to hydrogen. So working in concert, the two of these could actually be used in a cell to take water to hydrogen. Okay? And that would be a big step in powering the hydrogen economy. That's something we're beginning to look at. Okay? So I don't want to give you the impression we're the only group here working on this, or the only group in the world working on this. There are a lot of really talented groups out there. Groups in Europe here looking at electron transfer, in the United States as well. Several groups across the United States, including MIT and the University of Connecticut and Oak Ridge National Labs here in the state of Tennessee and University of Tennessee. But working on different aspects of this, whether it's immobilization, whether it's making electronic devices, whether it's making different kinds of photovoltaic type materials out of Photosystem I. So it's tempting to look at all the really talented people and groups working on this and get a little bit depressed, basically with the attitude that I show my students. If you're not a winner, then by this you're a loser. And so, but we don't want to be the losers here. We want to be the winner, or certainly one of the winners here. And what I'm going to do now is kind of take you back through the early years of this project, some of the real obstacles we encountered in trying to get to the point we are today. So our first paper came out in 2004 in Langmuir. Basically, what we were able to show in that paper is that we could identify surfaces and test surfaces that allowed Photosystem I to absorb onto that surface, and we could find surfaces, prepare them that did not, basically that prevented the protein from absorbing. So imagine this is useful because if you can do that, you can get protein to go here and here, but not here. Okay? And that's exactly what we did in the second paper, is we showed that you could direct where this protein goes on the surface. So Photosystem I was, and so this is one of the figures of that paper. The white region here shows an area where Photosystem I was able to go. The blue region was with a hydrophobic molecule that prevented Photosystem I from attaching. And so we saw regions that are rich in Photosystem I and regions that had none. Now, but I want to mention, in the early work we did, we could not measure any photocurrent. Okay? We were trying to measure photocurrent, putting proteins on a surface, and we would run the tests and would come back either with zero current or so little that we really wouldn't want to brag about it. Okay? So that led us to thinking this. Didn't want failure to become our style. So we worked very hard. When that happens, you just have to work harder. Okay, and so we learned a lot over the next 2 or 3 years there. Okay, we learned that we could increase the potential and force electrons into Photosystem I and really kick off this process and enable photogeneration. we knew that the orientation of the protein was very important, and we became more convinced of this with the other work that we were doing along that time. The attachment of PS1 to the surface. Basically how long that attachment is, the longer it is, the harder it is to get electrons up in the protein. Whether it's covalent versus physical, covalent interactions provide essentially a molecular wiring for electrons to go right into the protein. Okay? So we investigated with a lot of that. Physical interaction versus covalent, discovered covalent gave us a lot better results on average. The other thing that was important, though, was surface coverage. Okay? You can look at this plot right here, and it's basically the photocurrent we're able to measure on the y-axis versus the coverage, if you want to think of that x-axis as the coverage of the protein on the surface. The dashed line there running vertically represents the point where we're getting very close to a monolayer. Okay? We're starting to approach a monolayer of protein on that surface. And what you see is the photocurrent is essentially negligible until we get very close to a monolayer in thickness of the protein. And basically at that point, all of a sudden, going from half a layer to 2/3 a layer to a full layer, we have a lot of photocurrent. Okay? And we did this by two different approaches, two different ways of assembling the protein. We found very similar results in each approach. Okay, so those are some of the highlights. We're actually starting to measure photocurrent for these systems, something that was certainly measurable and quite a bit of photocurrent at getting us up into the hundreds of nanoamps. Now, but I want to point out that if you have a monolayer of protein on the surface, you're essentially limited by the absorption of light, the absorption of light. A monolayer is only going to absorb a very slight fraction of the light that comes to it. Okay? The rest is going to be reflected away. So from an overall standpoint, you're not using much of that energy that's coming into the system. The other aspect of this is that because your photocurrent is essentially electrons transferred into and out of the protein, you need to have a lot of interfacial area, essentially, for the light that's coming in. You need a lot of surface area so you can get more electrons going into more proteins and ultimately get more current. That was a problem. If you're using a flat surface, you just don't have much surface area or interfacial area for this to happen. And so the first way we wanted to basically solve the problem was to go to a nanoporous electrode. Rather than a flat electrode, we have limited interfacial area. Let's design pores. Let's put the proteins throughout these pores. And then for light coming in at a geometric area, there are a lot more proteins. There's a lot more area to transfer electrons. Okay. The second thing we did, I'll talk about later in the talk, is ultimately can we build thicker films of protein that absorb more light? And then somehow through that, can we get greater currents in that process? Okay. So let me go first into the nanoporous type systems. So, saying you want to do nanoporous electrodes and put protein in is one thing, but actually achieving it is something else. We struggled a bit with defining and finding the right types of nanoporous systems to work with. Ultimately, we decided that we could use something called nanoporous gold leaf. And we actually developed a new robust way to make electrodes from nanoporous gold leaf that was not in the literature when we started this process. So nanoporous gold leaf occurs in the following way. You basically go to the artsandcraftstore.com, no kidding. You buy something called gold leaf. It's a 50-50 alloy of gold and silver. It's about only 100 nanometers thick. It'll kind of float on the air as it falls down. It's very delicate, very fragile type material. Artists use it quite a bit. That's why it's sold at fineartstore.com. Artists will use it to place on paintings, to give paintings kind of a metallic look at times. Well, so we bought this gold leaf, and I thought it was a joke. I was like, there's no way this is going to work. And one of my students had a lot of confidence that this would actually work. And so what he developed was a process to make it work. We took the nanoporous gold leaf on a glass slide, dipped it in a beaker of nitric acid. The nitric acid pulls out the silver, creating a porosity inside the structure. The gold is left behind, and you have this nice porous gold structure. Then we take it out of the nitric acid to rinse it. And then we actually attach it to an electrode surface through a chemical interaction. If we're attaching it to gold, we will use what's called a dithiol. Sulfur's on one end, sulfur's on the other. They interact with both ends of this. And you create, from this delicate 100 nanometer structure, you create a robust electrode that you can use that's supported on a glass or silicon wafer. You can use it for a lot of different studies. We can also do it right on glass. So you change the surface chemistry, you use a group that connects to glass rather than to the gold, and now you're connecting to glass on one end, gold on the other. What I like about this processing is that it's simple enough that you're your golden retriever can do this. Okay, so it's a nice process, and it's easy to make these higher surface area materials in a very straightforward way. This is what it looks like. If you look straight down on it, you have now the gold and then the porosity that's built into the structure. So that's a 300 nanometer scale bar there, giving you an idea of the size of the pores at this particular sample. That's looking side view on this. So you have the nanoporous gold deposited on top of a surface and some porosity built in that. What we like about it, aside from the simplicity, it's 100 nanometers thick, so it's very easy to get light penetration into the structure. There are other options out there that are much thicker, and so you'd only be getting light or radiation into the top fraction of the surface. And we wanted to radiate the whole structure here. We have to then attach the proteins into the structure, and so we do that through a covalent coupling. We first put a terephthaldialdehyde group onto the surface by reacting that with an amino-terminated surface, and then we expose it to the protein. The protein will have a lot of lysine groups, amino acids terminating with a dangling amine, and those will react with this dialdehyde group there to ultimately form an imine linkage. Okay? And so we're able to bind the protein in this way. One thing I failed to mention, this nanoporous gold leaf is actually fairly cheap too. Because it's only 100 nanometers thin, it's about 6 cents per centimeter squared. So it's not like we're really breaking the bank by using gold here. We're able to do it in an affordable way. Okay, so let's see how this works. The blue here is a flat gold electrode that we have in the dark, and then we turn the light on, and we see how much current it produces. The red is the nanoporous electrode. Notice that the nanoporous electrode wins here. We get a lot more. We get about 4 times more current from the nanoporous electrode. I would tend to be optimistic about that and say victory, but there's one problem, is that the nanoporous electrode we used here had an 11-fold greater surface area. So why don't we get an 11-fold enhancement? Why is it only 4? Okay, so that was, the pessimist in me worried about that, and I think it's better to be pessimistic because of this right here. If you're optimistic, then bad things can happen. So we then decided to figure out why we didn't get the 11-fold enhancement. What's going on here? So we can change the surface area of these structures by the extent of time that we dealloy that gold-silver alloy to basically pull out the silver. The longer we dealloy it, the bigger the pores get, as shown there. And then the surface area gets reduced as these pores get bigger. Okay? So now if you look at photocurrent, after you put the protein inside, notice that initially we have the blue first bar there, we have a lot of surface area. We don't have much photocurrent. As you move forward, our surface area goes down, our pores are getting bigger, our photocurrent starts to rise. And by the time you get out to 24 hours, we now have a photocurrent that matches the surface area on this. And so at that point, the pores are big enough to get this protein in and to utilize all that area that we created in that 100 nanometer thick structure. Okay? So take-home message here, the pores have to be plenty big enough, and plenty means significantly greater than the size of the protein on average to be able to utilize that type of structure. Also, I show you here, if I plot the normalized current versus the light intensity. As we increase the light intensity here, we get more photocurrent. The blue is just for a flat, planar electrode. The red is for this nanoporous gold leaf electrode. And you can see the slopes here are different. That's because we have better integration of protein in the nanoporous structure. And so as we increase that light intensity, we get more and more current at a steeper slope, which is very good. Notice the light intensity here, though. It's still pretty low. The average light intensity on planet Earth is about 340 watts per meter squared. So we're still way shy of that. And for our nanopore system, we're already pushing toward a microamp per centimeter squared for just a monolayer of protein. Okay? So this is an important result that shows that we're really building better and better systems here. I want to switch gears just a bit to now talk about building thicker protein films. Okay? And then can we utilize those to ultimately achieve more and more current out of these systems? So this shows our process for doing it. We start with a PS1 suspension on a substrate. We apply vacuum here to actually remove the water and concentrate the protein. A normal protein, you couldn't do this. Proteins will denature like crazy when you start applying vacuum to them. But PS1 being a membrane protein, very, very stable protein. So we can do things with this protein that you couldn't do with your common protein. We apply the vacuum, remove the solvent. We get we can get a fairly thick multi-layer film, thick by our standards, by the way. Thick by our standards is a few hundred nanometers to a micron, and that may not be thick by everyone's standards. But here, this is what it looks like. This is about a 3-micron film of Photosystem I, a side view of that. This has gone through a few of those deposition steps to build up. I think it's about 7 deposition steps, gets us to about the 3 micrometer range. Okay, so you can think of this kind of like a leaf plated out on your surface, except rather than have all the components of the leaf, we've just got the one component we really want. Okay, we've just got the Photosystem I concentrated, densified in this type of structure. We have a bit of control over the film thickness as we deposit this protein. As we do more deposition steps, we get more thickness, of course, and so we get kind of a linear trend there with steps versus thickness. I want to point out, too, as we do a deposition step, we're actually getting much more than a monolayer of protein. The slope there suggests almost 400 nanometers of protein deposited per step. Okay, so we're talking then roughly 40 layers of protein at a time that we're able to put down by this method. The more protein leads to greater absorption of light. And so as we build these layers up, they do absorb more light. 1 layer down there at the bottom all the way up to 7. You still see the characteristic signal of Photosystem I, the green region there in the middle. We have kind of a valley. We're absorbing well in the blue and the red. And then to go a step further here with this, ultimately the amount of photocurrent that we produce is dependent on the number of deposition steps. So here, going from 1 up to 7 again, you see we have increasing amount of photocurrent, and increasing the thickness of this film. At first, we didn't really know what was going to happen. You still have your 1 layer of protein down at the bottom that's ultimately interacting with the electrode. But here, going to thicker and thicker films, we get more current. Now, I want to mention, we didn't really see a ceiling on this process. I think the student working on this kind of lost patience after 7 steps and didn't go any further. But the nice thing here is this keeps on going up over a number of steps. And so we're able to see these enhancements in current, which we've attributed to basically gradients of the mediator near the electrode that are created during this process and ultimately give us these nice currents that scale very well with thickness. We've also made, through this process, a kind of a handheld photoelectrochemical cell, and very crude. I'll show it there at the bottom. It's just essentially a glass substrate on bottom, some gold-coated silicon wafers in the middle, an indium tin oxide glass coating on top. We put these together in series. In this case, they're actually in series. Look, they're in parallel. They're in series, running through, and we clip them all together with some simple clips and shine light on it, and we are able to get some curves there. The curves I showed there are actually from one single sample, not the 5 in series there. And so we're able to, when we shine light, see open circuit potentials that rise up. We're able to see currents that rise up as well. For the systems I show here, putting them all together increase the potential that you're able to measure. You're able to ultimately get, I think the best we've done, and something that you can hold in your hand, is about 600 millivolts, which is about getting close to half the voltage of a AA battery from something you can hold in your hand from these. We can power simple calculators out of these systems. Okay, so a simple grocery store calculator you can pattern, or you can power with these types of protein-driven cells. Another thing I want to show you as well that's important for these types of devices, that they are actually more stable than you might think. When David and I were first writing proposals, we got shot down quite a bit by having, say, one person on the panel that said this will never be stable more than a week. Okay, and so it seemed like we'd get 3 really good reviews and one that said that, and we wouldn't get the funding. And so we kept working, and ultimately we worked on, let's make a real cell you can hold in your hand like I just showed, and let's see how stable this cell might be. And so this shows you then what we did here was we made the cell. We exposed it, basically, so it's in a liquid-like cell, as shown in the last figure, basically. We will test that every day at the start of the period, and then we test it gradually as time goes on. And so here I'm showing you up to 280 days after fabrication. And the X's here represent the photocurrent we're able to achieve at those times. What you'll see is that we started out really well, 4 microamps. Day 2, we hit a maximum of 7. We then settled for days 3 through about 12, 15 into a very nice rhythm there of a little over 3 microamps. We started to see some decrease between, say, day 15 and day 100, and ultimately discovered, after day 100 there, the minimum, that we had a bubble in this cell. Who would imagine that such an expertly crafted cell would have a bubble? But we did. We had a bubble. And the student, though, found that just by injecting fresh electrolyte to displace the bubble, we're able to pop right back up into kind of an acceptable regime. And we were able to take that out. And even the last days there, the last day tested at 280 days, is back up there where we were generating a very stable 3 microamp current from, say, days 10 to 100. Okay? So we're able to show that this type of cell can be stable. And you might say, well, I can imagine it being stable over the growing season of a plant. Yeah, but this shows it going further than that. Okay? And the fact that it's still pretty level with where we were after the first few days suggests that things can keep going on further and further. There had been a group in Japan tested one out well over a year, and it was also stable for a while, so over that period and beyond. So you know, these are not limited to the season of the plant. Once you take it out of the plant and once you densify it and put it on a surface, essentially it's protected. It works very well over a long period of time. I want to put this up. You know, what I want to do now is transition a little bit from what we've done, what we've published. In the last few slides here, I know people got to leave to go to receptions, but in the last few slides, just show a little bit about what we have done very recently and where we're kind of trying to go with this. And so this slide I'll put up. This is from Matt Irwin, who's here in the audience. And Matt did his senior thesis on this project. And one of the things that Matt was investigating here in the last semester was, can we irradiate for longer periods of time? Importantly, though, can we marry PS1 to the nanoporous electrode, a multi-layer PS1 film to the nanoporous electrode? Earlier I showed you a monolayer protein on the nanoporous system. Well, he's looking at thicker films on the nanoporous system. And so the idea was we get an elevation for the thicker film, we get an elevation for nanoporous, we put these together, can we really see a great enhancement? And the other thing he investigated here was kind of the effect of the mediator concentration, these small molecules that kind of go between the proteins and the electrode. And so he's increased that mediator concentration. So this is all preliminary results, nothing we've published, nothing we're ready to publish anytime soon. We've got to understand it a lot more. But the nice thing here is that he sees some currents that are quite impressive. So photocurrents now, before I showed you a maximum, I think, of 10 microamps per centimeter squared. Match results here show us going up to, if you take, say, the line, connect that blue curve connecting the line to the other, an average, you're talking about maybe 200 microamps per centimeter squared there. Oh, thank you.
Just the top one.
All right. So basically about 200 microns per centimeter squared, and we kind of connect the baseline there. So a great deal more photocurrent than what I showed you for the other systems. And so this is something we have to look into a little more before we can publish it, but I think it's a very encouraging sign as we move forward. The other thing I want to tell you about just is something that we've gotten started in the last few months, and that is basically, it connects back to the beginning of the talk when I said, can we generate hydrogen? Hydrogen will be a fantastic fuel for the hydrogen economy. Can we generate that using Photosystem I? Ultimately, maybe with Photosystem II and other things. But right now what we're doing is we are designing a thick PS1 film. We are photoreducing platinum into that film because platinum is an outstanding catalyst for hydrogen, production. And so this is our PS1 film, now with platinum deposit. The white areas you see here are platinum. Right? And the test here, so Gabriel LeBlanc made these films, and Gong Ping in the audience here tested them. And so what we're doing is we're testing it with scanning electrochemical microscopy, where we take a tiny electrode and raster it over the surface. And that electrode can actually do electrochemistry through solution back and forth with the platinum particles that are deposited on the surface. So with that technique, we're able to detect where we have active Photosystem I connected to platinum on the surface. Okay? And so what we see here is that the result of this kind of mirrors what we saw in the image here, the SEM image, in that you see hot spots. Okay? The red here would indicate we're generating quite a lot of current. We're seeing that protons are converted to hydrogen back and forth between the tip and the platinum on the surface. And it kind of mirrors this because you don't see platinum everywhere here. It's not a sea of white. But what you do see are these hot spots where we're really generating quite a bit of photocurrent or using that to generate hydrogen. What we'd like to see moving forward is this whole area become red. Okay? If that whole area becomes red, then we will have a lot of active Photosystem I platinum complexes that are able, with light hitting them, to convert protons to hydrogen. Okay? And you'll see a lot more hydrogen being produced, and you'll see this start to really, really make some great news. So my last words to the seniors are this, I think. Basically, what I would say is I've really enjoyed working on this project for the last 9 or 10 years. I do, in contrast to that, though, I do think we've learned to do it rather well. There were times when maybe we were struggling, but I think we're learning to do it quite well. As kind of evidence of that, I'll put up my final slide, our conclusion slide here, which really shows you on a log scale the first photocurrent we ever reported back in 2007, not too long ago, at 4 nanoamps per centimeter squared. And the photocurrents we've reported since in 100, 400, 2 microamps, 10 microamps, and then the unpublished result I showed here that we have to look at a bit more, but 200 microamps. Okay, so that's roughly 5 orders of magnitude we've done in less than 5 years. Okay, so I like that. I like that trajectory. I like that trend, and I've really enjoyed working on this, and I've especially enjoyed talking with you today. So please let me know if you have any questions at all. I'd be happy to answer them.
Technology developed become like stored energy that can be converted later, or
yes.
Dynamic system that has to keep it evolved.
Yes, stored energy is something that would be very interesting in today's system. And that is something that we've talked about, and my collaborator is an expert in terms of nanoparticles, and basically you can connect, the idea is you should be able to connect the photosystems to nanoparticles to actually store energy and then release it on demand. That's something we have not demonstrated as of yet for this project, but it's something that will be, I think, very interesting, is shine light, store that energy up, and then use it as you need it. Very nice. Yes?
Is the original monolayer, and then you did the vacuum deposition, do you just need the